in the next couple of chapters. Okay, so we want to be able to describe three-dimensional motion. Okay, and of course, like I like to say, how do you eat a steak? Yeah, one bite at a time. Okay, so what we'll do is this chapter will just describe one-dimensional motion. Okay, so we'll do one piece of that. Okay. All right, so let's do that. So for instance, here's, so one-dimensional motion means just motion in a straight line, along a straight line. So for instance, we would be interested in describing this motion. So here's a car, and then it's going like that. So here's the motion. Okay. How many different kinds of motions are possible? Infinite number of different motions are possible. Okay, so you can go like that, and okay, and that corresponds to how many different functions can you define? You can define an infinite number of functions. Okay, for every function that describes a motion. Okay. All right, here is a graphical representation of that motion, of one motion. So you see what it's doing is, so in this one-dimensional motion, there's the origin, there's the x-axis, positive x direction, and there's the negative x direction. Okay. So what is this telling you? It's telling you where the car is located at all times. See, at 10 seconds, the car was at 50 meters. At 20 seconds, it's at 38 meters. At 30 seconds, it's at 0 meters. At 40 seconds, it's at minus 38 meters, and so on. You see, for every instance, it gives you the location of the car. So essentially, it's giving you this. This is a graphical representation of that function. Okay, so this is a description of a motion, of a motion. So this is a description of motion. Of a particular motion. Okay. So somebody has given you this, and from this you can extract information. Okay. So there'll be two pieces of information you are in general interested in. You will be interested in the velocity and the acceleration. Those are the two pieces of information we'll be interested in. And if you sometimes you're interested in the derivative of the acceleration, that's called a jerk, but we won't be interested in that. Okay, so if you're all right, so here's another thing about these guys. Okay, what is a vector? It's something that has both magnitude and direction. How many numbers do you need to specify a vector? Okay. How many do you need in 3 dimensions? 3. What are those numbers needed for? 1 for the magnitude, 2 for the direction. In 2 dimensions, 2 numbers, 1 for magnitude and 1 for direction. Okay, so let's, now in 1 dimensions, the vector points either in that direction or this direction. Very good. So this is 5 meters per second, and that's minus 4 meters per second. Okay, so in 1 dimension, the direction is just given by the sign. You don't need a number. Okay, so the sign tells you the direction of the vector. All right, so you keep that in mind. All right, now, so I'm sort of giving you stuff that we'll learn over the next 2 chapters. Okay, so what did we learn now? If you want to describe a motion in 1 dimension, give me the x position as a function of time. Okay, so let me do an example. I'll just make up a function. Yeah. Okay, so here is a function. Okay, this tells you where the object will be located at all times. So at t equal to 0 seconds, it's at 10 meters. At t equal to 1 second, it's 15 plus 7, 22, 30, 40 meters, and so on. You can calculate where it is at all times. So you have a complete description of the motion. And like I said, once you're given the motion, you want to, you can extract all the information you want from that function. Okay. So for instance, you will want to know the velocity of the object at various times. And the velocity you'll learn in a second is the time derivative of the position. Okay, you guys, does everybody know how to take a derivative? Okay. All right, so here the velocity. The velocity is the derivative of t cube is 3t squared. So 45t squared plus 14t plus 8. And then you'll be interested in getting the acceleration of the object. The acceleration of the object is the time derivative of the velocity, which turns out to be the second derivative of the position. Okay. And so the time derivative of this guy is 9tt plus 4. Okay. Again, so that's what we're going to learn in the next two chapters. Okay. When somebody asks you describe a motion, what they're asking you is they're asking you for the position as a function of time. And then if you want to calculate the velocity is you just take the time derivative of the position. Okay. You get the velocity. And if you're interested in the acceleration, there's the acceleration. Okay. This is the acceleration. Okay. And that's what this next two chapters are about. You guys understand? Okay. All right, so again, we're starting off with a one-dimensional motion. Okay, so here is, so somebody's described this motion for you, one particular motion for you. They've given you this function. They have represented that graphically here. Okay. All right, so we consider motion along a straight line. The line can be vertical, horizontal, or slanted. It doesn't matter as long as it's straight. Okay. So right now, we are moving only along a straight line. Okay. If you move along a curved line, that's a higher dimensional motion. Okay. That's either 2 or 3 dimensional motion. Okay. So, okay. Forces cause change in motion. When you apply a force, you'll learn in a few chapters, when you apply a force on an object, the object will accelerate. When it accelerates, what does it mean when you say it accelerates? When it accelerates, its velocity changes. See, that's what this is. See, when you're accelerating, your velocity is changing. Again, so if your velocity was not changing, then the time derivative would be 0. Okay? So when you apply forces, but we'll learn that, then you will accelerate. That means velocity is changing. Okay. We consider the motion of particles. We consider the motion of point objects. What is that saying?
Every part of the object has the same velocity.
That's right. Okay. So we are keeping it simple. Every part has the same velocity, so you could treat this as a point object. This just became too complicated. Okay? So that's too complicated. We don't want to do that. Well, I mean, that involves 6 functions rather than 3 functions. All right. So here are velocity, acceleration, and displacement. These are vector quantities. So these are quantities about the object. Speed, pressure, these are scalar quantities. Speed is a scalar quantity. Okay? So here's another motion. So here's an armadillo walking along this path. And here's a description of this motion. Okay? How do I know that this is a description of the motion? Why do I say that this is a description of the motion? Yep.
So position versus time graph.
Yeah, it's giving you where the armadillo is located at all times. Okay, and that's what this thing gives you. See, if you give a function if you give the position as a function of time, what is it telling you? It's telling you where you're located at all times. Okay, and that's a description of motion. Okay. All right, so this is a graphical representation. This is a functional representation. Okay, so mathematically, a motion of an object can be described by giving the position as a function of time. Okay, so that's the key. Okay, that is what we are interested in. Okay. Okay, so we'll define various quantities. Let's first define a displacement vector. Okay. Now I'll do it for a more general case. Let's say let's say you went flying like that. This is your initial position, this is your final position. There is our initial, there is our final. The displacement vector is a vector from your initial position to the final position. And it is denoted by delta R. That is your displacement vector. Okay. So let's say you start from home, go for a walk, and come back home. What is your displacement vector? Zero vector. Okay. You walk to New York and come back. What's your displacement vector? Zero vector. You go to the beach and come back. Zero vector. Okay. So here we go. You go there and walk back. Your displacement vector is zero vector. Okay, so in this case, so this is the spatial coordinate and the time coordinate is shown this way just to show you that you initially were walking in this direction and then you walk back in that direction, okay, as time progressed. All right, so let's say you walk there and then back like that. So this is your initial position, this is your final position, and there is your displacement vector. Okay. So in one dimension, okay, so here is the displacement vector. There is the final position minus the initial position. Okay, so that's the displacement vector. Okay, and so that generalizes x is equal to x final minus x initial. So this is in one dimension. The way I showed you for 3 dimensions. So here, delta R equal to R final minus R initial. Okay, so it would be this vector minus this vector. That vector is this vector minus that vector. Okay, again, we'll learn that in the next chapter. Okay, so again, this is a vector. And this is the final position minus the initial position. Distance is a scalar. And again, don't get caught up in a lot of... Okay, so distance is a scalar. Okay. What was the displacement vector here? Zero vector. What was the distance that you walked here? 1 kilometer. Okay. What was the distance you walked here? 1 kilometer. Okay. The distance and displacement do not give you a description of the motion. They're just average quantities. Okay, so the displacement for this was 0, this 0, this 0, 1 kilometer, 1 kilometer, 1 kilometer, and so on. Okay, so those guys, they just give you an overall number, sort of an average number of the for the motion. Okay, they don't give you a description of the motion. All right. Now we'll define average velocity. Velocity is a scalar or a vector? Vector. Okay. So velocity is displacement divided by time. Remember, this is a vector. Time, change in time is a scalar. So vector divided by scalar is a vector. Okay. So average velocity is displacement vector divided by time. Okay. Now this is the average velocity, and again, units are, this is measured in meters, and that's measured in seconds, so units are meters per second. Okay, this is the average velocity, so you could calculate the average velocity over 10 hours, 15 hours, 5 minutes, 10 minutes, and so on. But generally what we are interested in is, what is my velocity at this instant? Okay. So when you're driving your car, your velocity, how do you find the velocity at this instant? You look at the speedometer, that'll give you a speed, and you know your direction in which you're moving. So that's how you know your instantaneous velocity. And mathematically what that is your instantaneous velocity is delta x by delta t in the limit delta t going to 0. Okay, so your instantaneous velocity is how much distance, what was your displacement in, let's say, 1 second, okay? And then that gives you, and then you take that, evaluate that for smaller and smaller time. In the limit delta t going to 0 is your instantaneous velocity. And you might have learned in your calculus classes that is dx by dt. Okay. And if you remember, so let's go back to functions. What does the derivative of a function give you?
Rate of change of
Rate of change of the
the function.
function. It is equal to the slope of the tangent line. Okay. All right, so dx by dt, all right, so if this is position as a function of time, if you calculate dx by dt, you can draw a tangent line at that point. The slope of the tangent line is your instantaneous velocity. That's what that is. Okay. Okay, so this is the average velocity. So if you calculate the average velocity between these two times, that's the chord. You calculate the average velocity between these two lines, that's the slope of that chord. And as the time interval gets smaller and smaller, you get the instantaneous velocity. Okay, so that's the instantaneous velocity at that point. Okay, so the instantaneous velocity is, you just go to the position versus time graph, draw a tangent line, and the slope of the tangent line at that instant is the instantaneous velocity. All right, average speed. So if you walked this 1 kilometer, the distance you traveled is 1 kilometer, okay? And let's say you did this in 20 minutes, so it would be 1 kilometer for 20 minutes. That would be your average speed. For this walk, what is your average velocity? 0 meters per second. Okay, so average velocity is 0 meters per second. Average speed and average velocity are not related, okay? And neither average velocity nor average speed provide details of the trip. Again, these are very, gross numbers about the trip. Okay? They do not provide any details about the trip. What we are interested in is the instantaneous velocity. Okay? What's your velocity at a given instant? So again, like I said, in your car, when you're driving in your car, to find your instantaneous velocity, all you do is look at your speedometer and you know your direction. Okay? So instantaneous velocity is given by dx by dt, the time derivative of your position vector. And at this time, if you wanted to find, so if you're given position as a function of time, if you wanted to find the instantaneous velocity at this time, all you do is go to the function, draw a tangent line. The slope of this tangent line is that guy. That's the instantaneous velocity. We did that in our example. So here is position as a function of time. There's your instantaneous velocity. Okay, so you can calculate your instantaneous velocity, your velocity at any time. Okay. And since your velocity was changing, you can calculate your acceleration at any time. Okay. Instantaneous speed is the magnitude of instantaneous velocity. So when you're driving, you look at your speedometer, that's your instantaneous speed. And that instantaneous speed and instantaneous velocity are related in the sense that instantaneous speed is the magnitude of instantaneous velocity. Okay. Acceleration is defined as when the velocity of an object changes with time, it is said to be accelerating. Okay? So anytime your velocity changes, you're accelerating. If your velocity is not changing, what is the acceleration? Zero. Okay, so right now we're dealing with one-dimensional motion, but okay, so let's say this is your velocity vector. Okay, are you accelerating? They're all supposed the same length. No. Okay. Are you accelerating? Okay. So you see you're speeding up, your magnitude is changing. And in this case, you learn that the acceleration your acceleration points in the same direction as the velocity vector. Okay? Are you accelerating?
Yes.
Yeah. Okay. This case, the acceleration is pointing in that direction. All right. So this is what we're dealing with in this chapter, but you'll deal with this stuff in the later chapter. So let's say now you're doing two-dimensional motion. Let's say we drive on a circular road at constant speed. Your speed is not changing. Are you accelerating?
Yes.
Yes. The direction of your velocity is changing. Okay? All right, so you are accelerating, and you will learn again, like I said later on, that this acceleration is pointing perpendicular to the path. This is called centripetal acceleration. So right now, what we are dealing with is only velocity where the magnitude of the velocity is changing. Okay? Later on, we'll generalize it where both the magnitude and direction of the velocity changes. Okay? So right now, what I want you to remember is, when are you accelerating? When velocity is changing. How do you change velocity? You can change the magnitude of the velocity, meaning you can change the speed, you can change the direction, you can change both. Okay, so there's many ways to change the velocity. Yeah. So remember that. All right. So you are accelerating anytime your velocity changes. Again, this is a vector divided by a scalar is a vector. Okay, what are the units? This has meters per second divided by second, meters per second squared. Okay. We are interested in the instantaneous acceleration. Instantaneous acceleration is dv by dt, and that's the second time derivative of the position. Okay. All right, so right now what we've learned is, when you describe a motion, when somebody asks you to describe a motion, what is it that they're asking you? I'm sorry? Yeah, position as a function of time. This is what they're asking you. And once you have that, what kind of information do you want to extract from this? Velocity. You want to know the velocity, acceleration. Okay? This will tell you if you are going to get a ticket or not. This will tell you if you're having fun or not. Okay? All right. So now, in the next two slides, what we're going to show is, and I'm not going to derive this because I have 8 minutes to finish this chapter. Okay. And all right, no, I'll just, okay. So this is what we ask of you. And if you have this function and this function, what is the information you can extract from it? Okay, so if you have velocity and the x just telling you, subscript x just telling you it's a x component of the velocity, and that's the direction we are moving in right now. Okay, so we are considering one-dimensional motion. And remember, this area under this curve is an integral, and that integral is equal to the displacement. Okay, so that's xt is where you are located at time t, and x naught is where you were located initially. Okay, so the area under this curve is the displacement. Okay, so the area under that curve from t naught to t is your displacement. Okay, I can quickly go over the derivation. Okay, so v, the velocity is dx by dt. Okay, so this is an equation. When you have an equation, if you hit this guy with a hammer, what do you have to do to this guy? He hit it with a hammer. Okay? So T1 to T2. And what is this guy? This guy is the area under that curve. And integrals and derivatives are, they're inverses of each other. So when you take the integral of a derivative, you undo that. So that's xt evaluated at t2 minus t1. And this is the displacement. Okay? What was your displacement for this time interval from t1 to t2? All right, so that's what this is telling you. So when you have velocity as a function of time, the area is under the curve is the displacement. When you have the acceleration as a function of time, the area under that curve is your change in velocity. Okay? We're just telling you what information is contained in those functions. Yep. Mm-hmm. I'm sorry? Oh. I am going to finish this lecture. I don't want to come back to this lecture, okay? So we might run over a few minutes, but You guys know half of you have labs, okay? And while it's working. Okay, we're doing a trip to UF, and we're looking to visit the nuclear reactor there and the hypergator. Uh, do you know what the hypergator is? I'm sorry? Okay, so it's the supercomputer that UF has, and that's the largest supercomputer on a campus. So those are the two things we're looking to visit. It's limited seating. If you want to go, send me an email, and I got about 10 seats left. So, um, and it's Friday, February 27th. We will be leaving here at 8 a.m. and we'll be back by 6 p.m. You just have to bring money for lunch, or you could be hungry. It doesn't matter. All right. So you see, here is a motion where the velocity is constant, and so you're not accelerating. Here the velocity is changing. How is the velocity changing? The magnitude is increasing, okay? So we are considering one-dimensional motion, okay? So here the magnitude is increasing, and if the magnitude is increasing, the acceleration is pointing in the same direction as the velocity vector. Here the magnitude is decreasing, the acceleration is pointing in the opposite direction, okay? You saw that acceleration was equal to dv by dt. What does the derivative tell you? The derivative gives you the slope of the tangent line, okay? So you see, here's a velocity that's changing with time, so it's obviously accelerating, but you see the slope of this line is not changing. The acceleration is constant, okay? The slope of the tangent line is increasing, that's the acceleration. Here the slope is constant slope, except that slope is 0 here. So that's the acceleration. This is what we'll be considering. We'll look at motions where the acceleration is constant. Okay. That's most of the problems we'll solve will be constant accelerated motion. Do you know an example of a constant accelerated motion? Yep. An object falling. Okay, so this guy, the acceleration of this guy is
10 meters per second.
very good. 10 meters per second squared. Okay. Can you maintain constant acceleration in your car? For about 3 seconds. Okay. But anyway, that's what we'll study. Okay. So acceleration will be constant. When the acceleration is constant, velocity increases linearly with time, and the position is a quadratic function of time. Okay? So this is a quadratic function of time, this is a linear function of time, so a polynomial of 1 degree less, acceleration is constant. Polynomial of 2 degrees less. Okay? So when the acceleration is constant, here is your position as a function of time. What this equation is telling you, xt, x naught is your initial position, v naught is your initial velocity, that's time plus 1/2 acceleration times time squared. Okay, when the acceleration is constant, position is a quadratic function of time. Okay, again, here's the displacement in terms of average velocity, but we won't use that too much. So we'll use these 3 functions. Okay. Velocity is a linear function of time. This is your velocity at a given time. Velocity as a function of time. Final velocity is initial velocity plus acceleration times time. And here's velocity as a function of position. Okay, so here's your final velocity square is equal to initial velocity square plus 2 times acceleration times the displacement. The further you have traveled, the faster you're going. Okay? These formula work, when do they work? I'm sorry? When the acceleration is constant, okay? If acceleration were changing with time, you can't use these formula, okay? Here's the derivation, I'm not going to do that. The freely falling object is one of the few examples where you see the acceleration is constant, okay? So what does it mean by freely falling object? What does that mean? I'm sorry? The only force acting on it is gravity. That is the only force that matters. All other forces are negligible. Okay, so in this case, the friction was negligible. Okay. In this case, it was not. Okay, so there are other forces. There's lift and so on. Okay, that's not a free fall. Okay. So when gravity is the only force acting on it, the acceleration vector is pointing downwards, and the magnitude of this acceleration is 9.8 meters per second squared. Okay. All right. So we have labs this week, and what we'll do is in lab we'll verify these equations. Okay. All right. I will see.